Last October, we helped brew the first beers on iron fuel. And this iron fuel was burned to produce steam, and that steam was used to brew beer, all without CO2 emissions. But where does the iron fuel come from?
Well, the initial iron fuel is made by using scrap metal. This metal scrap is melted in an electric arc furnace. Afterwards, the melted iron is atomized by using water jets, creating the iron particles. These particles are then dried and packed, and so the iron fuel is ready to be burned.
After the iron fuel is burned, we are left with iron oxide. And this can be regenerated into iron fuel again, with renewable hydrogen.
In the future, we foresee regeneration plants located at places with abundant and cheap renewable energy. We can then store and transport that cheap renewable energy to locations with high energy demand. In this metal energy carrier project, we investigate the regeneration of iron oxide to iron fuel and validate the iron fuel cycle. We examine 3 different regeneration methods in 4 setups at various operating conditions. Each method has its own characteristics and effect on the regenerated fuel.
Here at RISE, we work with realized bed reactor. In this reactor, the iron oxide particles interact with hydrogen flow fed through the bottom of the reactor, such that the mixture behaves as a fluid. This way, we achieve a lot of contact between hydrogen and particles, regenerating it into the iron. We also study the influence of the experimental parameters or conditions such as temperature and particle size on the regeneration process and on the properties of the resulting particles.
At Rift, we developed a reactor for the regeneration of iron oxide to iron fuel. This reactor validates our software models and business case.
The reactor operates at various temperature and pressure combinations, which enables us to select the optimal conditions for further scale-up, technically, but more importantly, economically.
Here, at Pometon Lab, we perform reduction trials of iron oxide using our belt furnaces. The oxides are placed on the belt conveyor that moves powder through a furnace, where it is heated to the high temperatures in the hydrogen atmosphere to create iron fuel again. However, the large powder volumes we regenerate using our industrial scale furnaces, which allows MEC consortium test high-capacity burners.
This reactor was designed for the Metal Energy Carrier project. In this reactor, we try to regenerate at temperatures of up to 1400 degrees Celsius. The iron oxide flows upwards in a stream of hydrogen, thereby regenerating the iron oxide to iron fuel. If successful, this might allow for faster regeneration.
Here, in this laboratory at Eindhoven University of Technology, we study the regeneration in a fluidized bed. The fluidized bed is ideal because of high mixing properties and high heat and mass transfer. We also collaborate with Solid and EMGroup on high temperature fast regeneration. The MEC project is essential to close the iron fuel cycle.
The first results show that regeneration of iron oxide to iron fuel is feasible. And with that, we have the proof of principle for the regeneration. Our current challenge is to better understand and optimize these processes for circular use of the fuel. We do this by investigating the properties of the particles in a series of combustion and regeneration cycles.
With every test we do, we get one step closer to making the iron fuel technology a reality, so that we can enjoy this beer produced with less CO2. Cheers!